last time we showed Rouché's theorem. And the idea is that you can perturb the function and still have the same number of zeros. So the thing is, if f and g are holomorphic on some region omega, and we have some disk D that is contained in the closure of the disk, and that is contained in omega, and C is the boundary of that disk. Then if I have that f of z is bigger than g of z for all z belonging to the circle, then f and f plus g have the same number of zeros. So we showed that last time. So here is just a simple example. So I actually looked today at a copy of Bader's exam from 2013 just to see what sort of questions were asked in the qualifying exam. So Bader actually asked this question. Okay, so good. Bader, Professor Bader, right? So this is basically to prove this theorem. It's one of the examples that you can have for qualifying exam. So just to illustrate how this is useful, what we do is let p of z, let's say, equal to z cubed plus 2z squared plus z plus 1, let's say. We show that P has all roots in the disk D3 centered at 0. So disk of radius 3 centered at 0. And here is how we can do that. Solution, so what we have is we can define f of t, f sub t at z to be equal to z cubed plus t 2z squared plus z plus 1, where t is in the interval from 0 to 1. Then the absolute value of ft of z is bigger than or equal to the modulus of z cubed minus t 2 modulus of z squared plus modulus of z plus 1. And because t is between 0 and 1, this is bigger than or equal to z cubed minus 2 modulus of z squared minus z minus 1. So then we have that if z belongs to the boundary of the disk of radius 3 centered at 0, that implies, of course, that the modulus of z is equal to 3. And that implies that f of t of z is bigger than or equal to 3 cubed minus 2 times 3 squared minus 3 minus 1, which is 5, which is bigger than 0. So the consequence is that f of 0 of z, which is just simply z cubed, has the same number of zeros in D3 0 as f of 1 z, which is z cubed plus 2z squared plus z plus 1. Okay? Now, you know that this one has exactly 3 roots. All of its roots are in the disk. So therefore, this one has all its roots in the disk. So that's just a primitive example of how you apply it. So there are always questions on the exam, on the qualifying exam that they give at the graduate center where they use Rouché's theorem. So either the proof of it or some application of it to some equation. I'm going to list a few examples for exam number 2. I'm going to write it over the break and send it to you, all right? All right. So let's look at the consequences of that theorem. So definition. A mapping f from omega to c is called open if it maps open sets to open sets. Okay? So you probably are familiar with this from before, right? So if a function is continuous, inverse image of open set is always open, but there are some functions don't have to be continuous. They map open sets to open sets. Thank you. Theorem, and this theorem is called open mapping theorem. Very important theorem that actually has more consequences than the fact that it's just open mapping, right? So we'll try to just see what is it saying. If f from omega to c is holomorphic and non-constant, then f is open. Proof. So let U subset of omega be open, and V which is equal to f applied to u. Just is the image of u under f. So what do we want to show about the set V? We want to show it's open, right? We want not the inverse. The inverse is another thing, right? So we want to show that this set V is open. So what we are going to do is, if f of z0, let's call this number w0, is an element of V, we wish to find epsilon greater than 0 such that the disk of radius epsilon around w0 is contained in V, which establishes that V is open. Right? So in other words, if I pick an arbitrary point in V, and an arbitrary point in V will have to be the image of some z0. Do you agree? Because V is itself an image of a set of the domain. Right? So let's consider how to do that. And again, pay attention to this thing, and we're actually going to make it very risky. So we see how far we can push it. So what we have is we will first pick a disk of radius delta around z0 that has its closure contained in U. U is open, so we take an open disk, and we take any open disk whose closure is also still there, right? So we kind of reach almost to the edge there. And what's important about this delta is that we want f of z to not be equal to w0 on the boundary of this disk. So how can we ensure that it's possible? Tell me. So you see I pick this disk around z0, and I can narrow it enough and be sure that on the boundary f of z never equals to w0. How do I know that? How do I know that I can squeeze the disk and there is nothing on the boundary that will equal to w0? The function is non-constant, right? Remember that thing. So it behaves like a polynomial. If you think about holomorphic maps, think of polynomials. Now polynomials actually are just a little bit boring because they take each value. If it's degree n, they take each value n times, right? So the inverse image of any point, they're always n roots. So it takes each value n times. So it has each value is taken finitely many times. Now, infinite polynomials, they can take each value many times, infinitely many times. But the points cannot, they cannot have a limit point. Remember that, right? The inverse image of any point under a holomorphic map cannot have an accumulation point, because then the function is constant. We proved that before, right? So the consequence is that if I take a ring and I zoom in around z0, I'm zooming in around z0, then that ring eventually must be free of images of points that are mapped to w0. Do you see that? Because if it's not, then there is a limit point, and then that would tell you that the function is constant.
Do we need to show at this point that w0 is not an accumulation point, or you can?
No, I mean you can just argue like this, but just know that we cannot have an accumulation point. So you can just mentally think about taking z0, shrinking the circle around z0, and then the circle eventually you must have some circle that avoids points of the form of z0. In fact, you can find a neighborhood in which only z0 is carried to w0, right? Because z0 must be an isolated point. All right. So next what we're going to do is we're going to figure out what sort of epsilon we want. So what we're going to do is let epsilon, which is obviously bigger than 0, be equal to the minimum of absolute value of f of z minus w0, where z varies over the boundary of the disk. We know that there would be a minimum because the function is continuous. Right? It's continuous on the boundary. And it does not take the value w0. So there will be some positive minimum. And that would be my epsilon. And that's basically the biggest epsilon I can take. I mean, I'm being very risky here. That I selected the biggest epsilon that I can take. Yes, so what we then have is if W belongs to the disk of radius epsilon around W0, we have the following. We want to know if W is in the image of F. Let's try to see if W is in the image of F. So what we do is we are going to calculate absolute value F of Z minus W. Yes, I pick this, and I want to know if F of Z minus W will ever be equal to 0. So absolute value of F of Z minus W is equal to absolute value of F of Z minus W0 plus W0 minus W, which, if I apply triangle inequality, this is bigger than or equal to F of Z minus W0 minus W0 minus W. Yeah? Which is bigger. So this part is what? This part is bigger than or equal to epsilon. You agree? And this part is strictly smaller than epsilon. So this is strictly bigger than 0. It's bigger than 0. Okay? For all, and this is basically for all z belonging to the boundary of the disk centered at z0. You agree? You see what I do? I know that the distance of f of z to w0 is epsilon. That's the closest I can come. So then I'm going to select w. I'm going to push it within epsilon from w0. And using this inequality, that's kind of I just barely make it, right? I just barely made it, just slightly more than 0. But what does it imply? By Rouché's theorem, by Rouché's theorem, f of z minus w0 has as many roots or zeros as many roots, I should say, in the disk. as f of z minus w0 plus w0 minus w, which is f of z minus w. You see, I added those functions. See, here are the two functions that I add. So what does Rouché's theorem say? Rouché's theorem say that that if this function is bigger than this function, then this function has the same number of roots as the sum. And the sum happens to be f of z minus w. Right? So for example, we'll see also what there is even stronger than so the implication is there is at least one root, since f of z minus w0 has at least 1, 0, z equal to z0 solves this equation, right? We know that f of z minus w must have at least one root as well. And the consequence is that W belongs to the image of the disk, which is a subset of the image of the entire set U, which is V. Yeah? I mean, this is just showing that there is a root, but let's just see for a moment. Suppose that this sub 0 is of multiplicity 2. How many solutions are we going to have for this equation? So let's say that if I analyze the f of z minus w0, if I analyze this function, I see that I can factor z minus z. So I can factor z minus z0 squared from this function, right? So what does it imply about f of z minus w? How many solutions will I expect to have? This is the most you can factor here is z minus z0 squared. So that has multiplicity 2. How many solutions will I have here? Two, right? The same amount. That's what Rouché's theorem is saying. You have the same amount. So then it may be I can factor some z minus z1 squared, or I can factor z minus z1 and z minus z2. Both things are solutions. So maybe z1 makes this equal to 0, and z2 makes it equal to 0. Right? So maybe there are two distinct roots, or there are one root with multiplicity 2. But you would have the same number of roots. That's pretty important. Make sense? Make some sense? It's a bit magical. I mean, right? You just you just investigate around the boundary, and then you figure what's happening on the inside. All right. So again, just try to prove it several times. Try to prove this thing, and just see that you understand the mechanism. So here is another very important theorem. This is called maximum modulus theorem. Maximum modulus principle. And what it's saying is if f is non-constant holomorphic function, in a region omega, then f cannot attain a maximum. In omega. So it's up to you. I can give you two proofs. One of them is a consequence of the open mapping theorem. So once you know the function is open, this is actually a very obvious result. And you can do it directly from Cauchy's theorem. So proof, what we're going to do is let Z0 be any element in omega. And the implication is that f of Z0 is an element of the image of omega in the complex plane, where f of omega is open by the previous theorem. Right, so we have this region. The region is an open set. F is a non-constant holomorphic map. This must be open. So what's the consequence? The consequence is that we have a disk of radius epsilon around f of Z0 that is a subset of f applied to omega for some epsilon. So, I mean, from here, let me just draw you a picture because I mean it's really a lot of words. But here is now a picture of what's happening. So this is my f of Z0. This is radius epsilon, right? And this is the region omega, right? So I found this open ball inside. Now I'm gonna just by drawing, I'm gonna show this cannot possibly be the maximum, right? Again, maximum. I should mention maybe in this thing not f, but absolute value of f, because f is a function from R2 to R2, right? So better said absolute value, right? Because I mean, what do I mean by maximum of f? Since it's from R2 to R2, I mean, we don't have an ordered field. R2 is not an ordered field, right? So this is f of Z0. So then what I can do is I can trace f of Z0 to the origin, right? And then I can continue until I reach the boundary of the circle, right? And I can just select some point here and call this f of Z, right? So what do you observe in the picture? Just looking at the picture, what can you say about the modulus of f of Z0 as opposed to the modulus of f of Z, the one that I labeled here? What can you say? Well, it's very obvious. This is the modulus of f of Z0. This is the modulus of f of Z. you can see that f of z0 was not a point at which the modulus was maximized. So you see what happens. I mean, the idea of the maximum modulus theorem, it's trivial theorem if you know the open mapping theorem, right? It's not obvious. I'm on the fence. I actually want to give you direct proof, cautious proof. But if you know that holomorphic maps are open maps, then this is very obvious. Because what you do is here is omega. Here is actually not omega. Sorry, this is the image of omega. Yeah, sorry. This is the image of omega. So I take the domain, I take the region, I map it somewhere in the complex plane under F, and I get an open blob. So any point in that open blob could not be one that maximizes the modulus, because pick a point in the blob, like this one, you can draw a disk centered at it, and then you can just trace where the point is relative to the origin, because that would be the modulus. And then you can, of course, just if you trace it back there, you can go forward. Right? There is, by the way, also, if you look at it, there is also here a minimum modulus theorem. Basically, what can you say about the minimum? Can the minimum be attained? What do you think? It's actually slightly dangerous. But look at this picture. I called it the maximum modulus. I claim that f of z0 is not the maximum. So the consequence is that modulus f of z0 is not maximal. So therefore, the modulus does not attain a maximum over the region here, right? Does the modulus attain a minimum in the region? Well, I mean, in this picture, let's just look at this picture. Here's f of z0. Is f of z0 possibly the minimal modulus here?
No, not in this picture.
Not in this picture. Why? Because what you do is you take this point and you go back, right? I mean, you're inside of a disk. You can go straight. You can just take this point, trace it to the origin, go forward or go backwards. So that would not be the minimal value. The problem is when you take the modulus, sometimes, I mean, what you can get is this point might be centered at 0. Right? So if f of z0 happens to be equal to 0, then when you take the absolute value of it, that would be the minimum. You understand that? I mean, basically, if you take absolute value and you get some points where zeros, like this picture, you know, this picture tells you that f of z0 is not 0 because it's not at the center of the xy axis, right? So the minimum modulus theorem is very similar. In general, you cannot attain a minimum inside of the region unless this point is equal to 0, right? So if a function is non-zero, in other words, if the image of omega under f if this image does not intersect the origin, then you can apply the minimum modulus theorem. There is no minimum inside of omega. You understand? Because if 0 is there, then trivially there is a minimum, right? The modulus can never be smaller than 0, and you can get 0. So if I just had this point centered here, in this case, in this region that I drew, the minimum modulus theorem does not apply. Why? Because it contains 0, so there would be a point here, right? So the minimum can be attained on the inside. But if I notice that the image of omega under f avoids the origin altogether, then there is also the minimum modulus theorem.
But minimum modulus, do we have to have f equal to 0?
Well, the statement is if the function is non-zero, in other words, if the function never vanishes over omega, you would just say that you would just make the same statement, and you just say f is a non-vanishing, non-constant function, right? Then over the region omega, then the modulus of f never attains the minimum inside of region omega. Okay, but then you have to add the word non-vanishing. That's the thing.
But what I was asking, but does it imply that in the minimum case we have to have f taking a value of 0?
No, I mean.
Can we have a minimum?
Well, I mean, again, inside of the region omega, no, right? That's what I'm saying, no, because it's an open set and you can have this picture, right? So if you can entirely avoid this 0, then you will not have a minimum over the region omega. It might be on the boundary.
But I can make my disk arbitrarily very, very small, right?
Yes, but the point is that no matter how much you make the disk, you would have values that have modulus bigger than f of z0 and values that have modulus smaller than f of z0. Kind of draw a picture here, right? So kind of like that. Okay. So let me give you an alternative proof. Sometimes they ask you prove the maximum modulus principle, and usually when they ask that, they don't assume that you know the open mapping theorem. So just for that safety, maybe, or just to illustrate some techniques of how this works. Unless you would prefer me to move on, no? You don't prefer anything, right? I'm at your service, guys, I hope. All right, so alternative proof. So suppose that f of z0 is bigger than or equal to f of z on omega. That means that f of z0 is a maximum. And I'm going to show the function is then constant. Okay? Let there be a disk of radius delta centered at z0. That is a subset of the disk centered at z0 closed, which is in omega. By Cauchy's theorem, Cauchy's theorem in the disk, we have that f of z0 is equal to 1 over 2 pi I integral around the circle of radius delta centered at z0 f of psi minus z0 dxi, which implies that the absolute value of f of z0 is equal, if I just parameterize and say what it is, this is going to be the integral 1 over 2 pi integral of, let's actually say less than or equal. I mean, I'm applying Cauchy's inequality, 1 over 2 pi, 0 to pi, f of z0 plus delta EIT dt. So basically, your usual inequalities. Apply the absolute value, parameterize, and you get this. Right? Now, if you look at it, what is that? This is the average. You see that this is the average of all the values around the circle. Right? So this is the integral that represents the average value of f over the circle CD. Now, because f of z0 is assumed to be maximal, I can replace this function by the maximum value. So this is going to be less than or equal to 1 over 2 pi integral from 0 to 2 pi f of z0 dt, because this is by assumption is smaller than this number, right? So if I replace it, this is just a real valued integral, it grows. So what's the consequence? The consequence is that if I compare the integrals, I have that 1 over 2 pi. So you see those maybe before I even say consequence, what is this equal to? This is just equal to the modulus of f of z0. So those inequalities are all equalities, right? So the consequence is that the modulus of f of z0 is in fact equal to 1 over 2 pi integral from 0 to 2 pi f of z0 plus delta e it dt. So it's equal to the average. And the consequence of that is that 1 over 2 pi integral from 0 to 2 pi of f of z0 minus f of z0 plus delta eit dt is equal to 0. Since g of t equal to f of z0 modulus minus modulus f of z0 plus delta eit is continuous. It's a continuous function I'm integrating. We must have f of z equal to f of z0. This is really f of z equal to f of z0 for any z on the circle. So in other words, if you look at the circle, the modulus is the same as that of f of z0. So I mean, it's very tempting, actually. I actually, when I was writing it today, I thought I was done, because it's very tempting to say that the function is constant on the circle. But it's not quite yet done, because the function only has a constant modulus on the circle. So what we do next is we are going to say that since delta can be shrunk, and the same conclusion reached, in other words, this argument works for any smaller delta. Just take a smaller circle. The idea of this proof is here is that circle of radius delta, and then we can shrink and just select all other circles of smaller radius than delta, and we will show that on the boundary the modulus is always equal to f of z0. The modulus of f of z is always equal to the modulus of f of z0, which implies that modulus of f of z is always equal to the modulus of f of z0 for all z belonging to the disk of radius delta centered at z0. So the conclusion is that the modulus of f of z is constant in that disk. And remember, we had an exercise in homework number 1, right? By exercise of homework number 1, this implies that f of z is constant. It's again, remember the amplitude idea, right? So if it's constant, that means that you take an infinitesimal rectangle inside of the disk, and it had to be crushed, right? It had to be crushed to a point for this to happen, right? I gave solutions to that if you want to see how I solved it, right? So by homework 1, the implication is that f of z is constant in the disk. which then implies it's constant on the entire region omega. Which proof do you prefer? But the first one is, again, the first one is very easy, but you need to know it's open mapping, right? So, I mean, maybe if it's on the exam of sorts, then you just say, well, by open mapping theorem, we have this and that. So here is a corollary. Suppose that omega is a region with compact closure. If F is holomorphic, on omega and continuous on the closure of omega, then supremum of z belonging to omega is less than or equal to supremum of z belonging to the closure remove omega. I forgot to say of the modulus. Well, I can write the proof, but it's actually very obvious, right? What's happening here? So the set omega closure is compact, and the function f is continuous, and therefore the modulus of f is continuous. You agree? And therefore the modulus must attain the maximum. By maximum modulus theorem, where is it going to attain its maximum? On the boundary, right? Because it cannot be on the inside unless the function is constant. Right, so if the function is constant, then this is trivial. Then this is equality, right? If the function is non-constant, then this already includes the boundary. The open set is not important. Make sense? Okay, good.
This is a restatement of the theorem.
This is, yeah, I would say almost that, right? Just be really careful that you understand why it's you see. There is no guarantee that maximum modulus principle doesn't tell you that there is a maximum modulus. That's the reason this is slightly different.
So the continuity.
You see, basically you might never have a maximum modulus. And it might not be on the boundary. That's another thing. You see, if you look into Stein, I didn't include that example because I just wanted to move on. But you can have a region and even a function that is extend continuously to the boundary of that region. And the maximum is not taking place on the boundary. You understand? But what's the consequence? If the maximum does not take place on the boundary, you don't have a maximum. There's no other way. Because if it's not on the boundary, then it's on the interior. If it's on the interior, the function is constant. Make sense? So either there is a maximum and it's on the boundary, or there is no maximum at all. Or, of course, the function does not extend continuously to the boundary, right? Again, that's again another way of saying no maximum at all. But for non-constant functions, it can never be on the inside. And that's going to be very important when we talk about Schwarz lemma, sorry. And this is very, very useful thing. Maximum modulus theorem and sometimes minimum modulus theorem. There is one question that actually I want to assign it. It was on the qualifying exam a little tricky. It took me a while to figure out how to solve it.
This might not be the right time for this, but why do we talk about continuations in complex, but we would never talk about it in the real analysis? When you say there's an analytic continuation, you just mean that there's another domain where it's continuous. Why do we go through?
No, analytic continuation means that there is a bigger region containing your previous region where the function is holomorphic.
And we don't talk about these in real analysis either.
I mean, why don't we talk about it in real analysis? We do. I mean, we talk about it in differential geometry where you want to define a function globally from its definitions locally. That sometimes is done, right? So you want to define a function over a manifold, and you have a bunch of functions defined locally, and you stitch them together, right? So you do have what you call it partitions of unity, things like that, which are, I don't know where you group them in real analysis or somewhere else, but they are analysis type of things, right?
Okay, so this type of thing comes from having expansions locally.
Right. I mean, my experience is still, I would say, limited, but where I've seen this useful is, let's say, by expanding the domain, you can reach conclusions about the function. You see, if you look at it like this, if I look at something like this, I don't have the full panoramic view. It's kind of like if I look at New York, right? I look like this, I make a very small pinhole, and I say, what a beautiful city, right? But then if I zoom in, I see all the garbage, right? So that's the same thing. That's the same thing about analytic continuation, right? So this function might look complicated, or I don't know, but you expand it, and something about it is revealed. So I'm going to give you some examples that again you start realizing well how it works. There were some examples I think in the homework. Remember where you had a function holomorphic map defined on the disk. And then you, by using Schwarz reflection principle, right? That's what you call it, right? You concluded that the function is constant, right? That's an example of analytic continuation, right? So you had it in the circle. You saw that you can continue it beyond the circle by just first of all making it. I'm not sure how you did it, but I would say take the disk, make it the upper half plane, and then you can now you have a symmetric region. Now you can extend it to the lower half plane. Now you have an entire function, and therefore you conclude that your original function was constant. So that's an example where analytic continuation gives you important ideas.
So you're saying that we could, if we knew the maximum modulus principle, we could have gotten to the same.
No. I mean, I'm not sure. I'm not saying that. I'm saying that they're going to be combined with analytic continuation and other ideas. You can apply minimum modulus principle, maximum modulus principle to reach certain conclusions about those functions, right? And yeah, I mean, I'm gonna I think post a bunch of exercises, and I'm gonna write solutions. So don't worry if you don't get it. I'll trace. Hopefully, I'll get it, and I'll give you the right solutions, and you would understand how it works. Okay. So how much time we have? We have 10 minutes more? 15, right? Well, probably 20. Maybe. So. All right, so the next thing that we want to talk about is homotopies and simply connected domains, right? I kind of really don't like writing this argument. It was a torture for me, but yeah, I mean, you actually it's even good enough for you to just know the conclusion. But so homotopies and simply connected domains. So remember what was the key to Cauchy's theorem? Like when we had Cauchy's integral representation, and before that we had this fundamental theorem of calculus type theorem, right? Every holomorphic map defined in a disk has an antiderivative, has a primitive. Now, how did we do that? The way we did it is we showed that, what was the point of Goursot's theorem? The point was that if you take any, you can just conclude that if you take any polygonal path from point A to point B, the integral over that path is invariant. You can just change the polygonal path as long as you keep the points A and B fixed. The integral will be the same. You understand? So let's write something like this. Key to Cauchy's theorem in disk is invariance of integrals where from the disk to C is holomorphic, and gamma any path from alpha to beta. So again, if you draw a picture, here is the disk. If I fix alpha and I fix beta, I can take the integral along this path, or I can take the integral along this path. Right, so it would not matter. So if this is gamma 1, this is gamma 2. We know that for any fixed holomorphic map F, the integral over gamma 1 of F dz is the same as the integral over gamma 2 F dz. That's the invariance I'm talking about. Okay, so that was really the key idea. I mean, we just actually first reached the conclusion about polygonal paths, but once you have it for polygonal paths, you now have a primitive, and now it's true for all paths, right? So in general, you're interested in the case when is it possible to just slide this gamma, change it a little, and still have the same integral. So question is a general question. Given gamma 1, gamma 2 from alpha to beta, when is it possible to conclude that the integral over gamma 1 is equal to the integral over gamma 2, where F is holomorphic? So in other words, those paths are in the region where the function is holomorphic, and when can we be sure that that happens? So we make the definition of homotopy. So definition, we can say that alpha 0, alpha 1 from the interval AB to C are homotopic. In omega, if there is a function h from, let's say, 0, 1 cross AB into C, such that h is such that h of st is equal to gamma of s at t, is continuous, is jointly continuous in S and T. and t. What other conditions do we need? We need, of course, that h of 0 of t is constant, right? Is constant, and h of 1 of. But no, I'm sorry. I meant h of s. H of s at a.
That should be alpha.
No, I mean a here, right?
Oh.
A and h s of b are constants. And of course, you have, again, writing this is really annoying. H of 0 t is just equal to gamma 0 of t. H of 1 of t is equal to gamma 1 of t. Again, right, all this nonsense is just this picture.
How's your S changing?
How is my S? My S is varying over the paths, I think, right? If I didn't write something.
Constant, or is it alpha and beta then in that case?
So let's write this is our alpha. So again, not A, this is A and B. This is just a parameterization. You can make it, usually in topology, you make it also 0, 1, right?
Yeah.
So it doesn't matter, right?
Professor, what does it need to be jointly continuous?
Why does it need to be jointly continuous? Well, let's just a second. Let me draw it, and then I'll try to explain. So this thing is I want to say why not, but I'm just no. So this is gamma 1, right? And somewhere here is so this is gamma 0, and somewhere here is gamma 1, and you see you have intermediary curves, right? So you have some intermediate curves. So you see there. That's why the fact that there are constants at s equal to 0 and s equal to 1. When s is equal to 0, we are at this curve. When s is equal to 1, we are at this curve. So when you're doing homotopy, what are you really trying to intuitively capture? You're intuitively trying to say that you can actually think of all those curves as the same piece of rubber, right? So it's like a string that is stretchable, and I'm just taking this and I'm moving it, right? And I'm moving the string from here until it looks like that. I'm deforming it, right? So I'm taking this string like a rubber band, and I'm deforming it from here slowly, gradually, until it becomes this. That's the idea of homotopy, right? Now, why do you want? Okay, so why do you want it to be jointly continuous? Is that suppose I select 2 points S1 T1 and S2 T2, right? S1 T1 is some point here. S2 T2 is some other point here, right? If the distance between those points is small, the curve should be close together, right? So in essence, first of all, it's obvious why you want continuity for any fixed s. It should be continuous, because for any fixed s, it's a continuous curve, right? And for any fixed t, it's the motion that would be, let's say, if you fix some t. Let's say you fix some t. So this is the point at t on the first curve. Here it is later on, and here it is later on. So you should see that this, because you're moving this rubber band gradually, you're seeing that this point is sliding gradually. There are no jumps to it. Make sense?
Okay, but what's the meaning of jointly?
Maybe I'm overcomplicated. Jointly continuous means that the function is continuous. H is continuous. That's all.
Okay.
So if you okay, sorry, I thought you were asking something. More, I mean, in other words, h of st is continuous. Jointly continuous means that you see you could have a function that is continuous separately as a function of s and continuous as a function of t. But if you look at it as a function of 2 variables, it's no longer continuous. There are examples of that, right? So jointly continuous is just a word for saying continuous.
Okay, so
Sorry about it.
nice function.
It's a nice function, right? And this is why. All right. We have any more time?
5 minutes.
5 minutes. I'm not sure I can prove such a theorem in 5 minutes. Would you give me 10 minutes? No? You're not shaking your head like this, not like that? So I'm hoping yes. So here is a theorem. If f is holomorphic in omega, then so those integrals are the same whenever gamma 0 and gamma 1 are homotopic. In omega. Proof: let H let this be the homotopy. Be a homotopy. Since H is continuous, we have that K, which is equal to the image under H of the interval 0, 1, AB, is compact. And what the implication is because it's compact, there is epsilon bigger than 0 such that the disk of radius 3 epsilon, even closure, centered at Z, belongs in omega for any Z belonging to the region K. Well, I should say maybe not Z. Let's call this. Yeah, why not? Let's actually call it Z. So omega. For any Z belonging to K. That's right. So in other words, if I select, so the reason that happens is that if let me just draw a picture. So here is K. That's actually true about any compact set. The K probably would look, if it's a homotopy, it would not look necessarily like that, right? So this is a K, and this is the region omega. So you can think of compact sets. I mean, this compact set is isolated from the boundary, right? It's isolated from the boundary of omega. So I imagine there is a theorem that does it rigorously, but imagine that this K is ziplocked. So ziplocked, so what you do is you take this is the glad ziplock. And glad ziplock is that the distance here is 3 epsilon. You understand? So that's so there is a you can look into Stein. There is a elaboration of it, but this is really what's happening intuitively. Or you can use Lebesgue lemma. All right, so by uniform continuity, of H, pick delta bigger than 0, such that supremum gamma S1 of t minus gamma S2 of t is less than epsilon, when so the supremum is taken over all t in the interval AB. And this is whenever S1 minus S2 is less than delta. Fix S1, S2 with S1 minus S2 smaller than delta. Choose disks. The 0, the n of radius 2 epsilon, consecutive points. Z0, Z1, Zn plus 1 on gamma S1 and W0, W1 all the way to Wn plus 1 on gamma S sub 2 such that the union of D sub k covers both gamma S1 and gamma S2. And I'm sorry guys for the torture. And what you have is that zk plus 1, wk plus 1 belong to D sub k. So again, and of course we have that z0 is equal to w0, zn plus 1 equal to wn plus 1. So again, all those conditions, there's just a lot of words, but for something that is very easy to explain. So we have here we have those curves. So the top curve is, so this is gamma S1, this is gamma S2, and this is Z0 equal to W0. The common point, this is Z. Well, I'm going to label it as not as Zn because I want to draw a particular number of circles. So then you have circles of radius 2 epsilon that cover this thing. So here is one such circle. Here is another such circle, and here is another such circle. So this is D0, this is D1, this is D3. And then you see they have intersections, right? So because this is a connected region, there would be intersections. So there would be a point here. This is my Z1, and this is my W1. This is my Z2, and this is my W2. And this is Z3 equal to W3. Okay? So that's really what the way the circles are constructed. They are supposed to be inside of omega, and they cover. By the way, guys, if you need to leave, you don't feel pressure to sit through this, right? I really don't want to hold you. I'm just going to try to finish it and finish it on video. And yeah, you can watch it if you want to. You don't have to watch it if you don't. Sorry, guys. Almost done. So here is the consequence. We have those disks, right? So we have that on each d sub k, let f sub k denote a primitive of f on dk intersect dk plus 1, fk, and fk plus 1 are two primitives of same function f. And the implication is that you see, so on the intersection, on this region, they are, we use Cauchy's theorem on this disk, we construct a primitive, and over this disk we construct another primitive. The disks intersect, so they correspond to a primitive of the same function f, and the implication is that they differ by a constant. The implication is that f of k plus 1 is equal to f of k plus some ck, plus a constant. And what does this imply? This implies that the integral over S1 of f minus the integral. So I break it. I break the integral into from here, for the integral of the curve from here to here, from here to here, and from here to here. So what you get is the integral of the first function is just summation k from 0 to n fk zk plus 1 minus fk zk minus k equals 0 to n fk wk plus 1 minus fk wk. So what I'm talking about is this. Okay, so from z0 to z1, we have a primitive. So by fundamental theorem of calculus, this will be f of 0 at z1 minus f of 0 at z0. Right? And then over this segment, we have another antiderivative. So that's why we have a sum of those functions. Right? So we have this. And then I can rearrange the sum like that. So notice that those are very similar terms, and because I have this property here, I can just actually make it a telescoping sum. So if you make, you see, basically I apply this property, I can go from k to k plus 1 if I want to. So I can make it into a telescoping property, and the answer will therefore be that this is just f of n plus 1 z n plus 1 minus f of n plus 1 w n plus 1 minus f of 0 z0 minus f of 0, w0, which ends up being, this is the same point, so this is 0 minus 0, and that is 0. So the conclusion, the implication is that the integral over gamma s1 of f is equal to the integral over gamma s2 of f. Now you can go through repeated steps for finitely many steps, so from s1 to s2, from s2 to s3, and in finitely many repetitions of the argument, you will get that the integral of the first curve is equal to the integral of the last. So guys, sorry for holding you. In my head it was completely useless because probably I was rushing through it and I was not explaining it well. But then I figured I started, I can't shut up, right? So we'll see. All right, take care.